All right, we're continuing with chapter 1 in the geometry textbook. In this video, we're going to go through section 1.6, which is on perpendicular lines. So we've already talked about the idea of perpendicular informally in section 1.2. So let's take a look at what we discussed then. All right, any angle having a 180-degree measure is called a straight angle, an angle whose sides are in opposite directions. So here's a straight angle between this segment ST and segment SR. When a straight angle is bisected, the two angles formed are right angles. Each measures 90 degrees. So if we bisect this angle, that means we kind of cut the angle in half, split it into two equal parts, because you could split this angle up any way you want, by adding a straight side. But if you do it in the specific way where you cut the angle in half and you do this to a straight angle, so you can bisect any angle. You could bisect a 30-degree angle, but we're bisecting a straight angle, which would mean that it creates two 90-degree angles. In that case, the angles formed are right angles. And so what they're saying is it's not so much about the meaning of right angle. It's not about if it's bisected or whatnot, but a 90-degree angle is a right angle, is what they're saying. If you have a 90-degree angle, that's called a right angle. And one way you can create a 90-degree angle is by bisecting a straight angle, which I guess maybe hypothetically in all scenarios where you have a 90-degree angle, you can think about it as a bisection of a straight angle. But yeah, okay. So when two lines have a point in common, as in figure 1.23, they are said to intersect. When two lines intersect and form congruent adjacent angles, they are said to be perpendicular. All right, so, okay, the meaning of intersection is that two lines have a point in common. So both of these are intersecting. Line segment SV is intersecting line segment RT. So these are both intersections. Just this is a little bit different in that the two lines are extending infinitely. So here you have one pair of adjacent angles. Here you've got two pairs, or I guess you could technically say four pairs. Like these are adjacent, these are adjacent, these are adjacent, these are adjacent. So in the case where the two lines intersect and they form congruent adjacent angles, they are said to be perpendicular. And as a consequence, we're not officially stating this, but if two lines are perpendicular, then they're going to form right angles between each other, because the lines are perpendicular and the adjacent angles are supplementary. And so in that case, if they're equal measure, they have to both be 90. So okay, that's what we learned about the meaning of perpendicularity and straight right angles previously. So okay, section 1.6 starts by saying, informally, a vertical line is one that extends up and down like a flagpole. On the other hand, a line that extends left to right is horizontal. In figure 1.59, L is vertical and J is horizontal. Okay, so yeah, they're saying informally because, if we're looking at this plane here, and yeah, that's up and down, that's vertical, right? And then left to right, that's horizontal. But, if you think about more general 3D space, vertical makes sense. There's up and down, okay, but horizontal is becomes more ambiguous in 3D space because, I guess anything parallel to the XY plane is horizontal, but you can say that vertical is still up and down, but when you try and say left to right, what exactly does that mean in 3D space? And then actually vertical becomes more ambiguous when you think about, so if we could take any plane in 3D space, this isn't a plane, but hypothetically this could be any plane in 3D space. So if we're looking at this plane, looking straight at that plane, so this is vertical and this is horizontal. Well, that's not up and down relative to the z-axis. So that's why they're saying informally. But yeah, so just looking at a plane like this, the only context is just looking at a flat plane. Yeah, up and down you'd say is vertical, left to right is horizontal. And in that case, these two lines intersect to form angles of equal measure, which informally in section 1.2, we said that was perpendicular. So now they're going to give an official definition, But the official definition is pretty much the same as the informal definition we can see. So perpendicular lines are two lines that meet to form congruent adjacent angles. Yeah, same definition. So that the key terms here are that the two lines meet. So that means they intersect, and then they form the adjacent angles that, so any intersecting lines, if you have an intersection, you're going to form adjacent angles, right? That's when we talked about vertical angles. So these two are vertical. When you have two lines that intersect, there's going to be four angles. As long as the lines extend all the way through, there's going to be these four angles that are formed. But what happens is you have four pairs of adjacent angles. So these are adjacent, these are adjacent, these are adjacent, these are adjacent, and you have two pairs of vertical angles. Those are the angle pairs that aren't adjacent. Okay, so that's any intersection. Now, for the case where the adjacent angles are congruent, the case of an intersection where the adjacent angles are congruent, that's the meaning of perpendicular. Okay, so it means angle 5 would be congruent to angle 7, angle 7 would be congruent to angle 6, angle 6 would be congruent to angle 8, etc. Now, you might say, well, what about is there a case where maybe only one of those pairs is congruent and the other pair isn't? Well, I guess we're going to look at this more officially later, but that can't happen. If you have at least one for an intersection of two lines in any plane in 3D space, two lines intersect, right? So what I mean by that is you can, in all of 3D space, you can view any plane in any orientation. Like two lines are contained in a plane. So no matter where the two lines are going in 3D space, you can always, kind of rotate the whole 3D space and look at it like this. Look at it through the plane that contains the two lines. There's the adjacent angles and the vertical angles. So okay, when you have an intersection, if these two angles are perpendicular, so that means they sum to 180. Well, okay, we know then that the angles on the adjacent angles on the opposite side are going to be summed to 180, but the line going through here doesn't change orientation, so these are going to have to be perpendicular as well. Like another way you can look at it is we talked about vertical angles are congruent. So if these two angles are congruent, then but we know that 7 is vertical angle to 8, so 8 is congruent to 7. So like 8 must be congruent to 6. So it's the case you can't have intersecting lines where like just one of the angles is 90 degrees and the other angles aren't. They're all going to have to be 90 degrees or none of them are going to be 90 degrees. And we haven't officially proven that, but you can think about how that's true. Okay, so again, when they intersect, two lines intersect, and the adjacent angles are all congruent, and that's going to they're all going to be congruent. Every single adjacent angle is going to be they're all going to be congruent, or none of them are going to be congruent. It's only one of two possibilities. Then that means the two lines are perpendicular. Okay, so just notice though that we haven't the official definition of perpendicular. We haven't said anything about right angles yet. We know that if two lines are perpendicular, they're going to form right angles. We talked about that informally in section 1.2, but we haven't officially stated that yet. So if you wanted to be technically correct and say the definition of perpendicular, you wouldn't say that two lines meet to form right angles, even though that is true. You would technically say that when two lines meet, they form congruent adjacent angles. All right. Perpendicular lines do not have to be vertical or horizontal. In figure 1.60, the slanted lines M and P are perpendicular. So yeah, they don't have to be vertical and horizontal. That was just a kind of the fundamental way to illustrate perpendicularity with a vertical and horizontal line. But these two are perpendicular, right? And so you can one way to say perpendicular is you say in this case line M is perpendicular to line P. You can say that. And another notation is the angle. You put like a box like this. You say, so these two lines are perpendicular. You could do it on either side since these two angles are congruent. These two adjacent angles are congruent. You could do that. You could do that. Okay, but then as a consequence, that means these two angles are going to be congruent on the other side. They're all going to be congruent, so you could do this as well on any angle you want. All right, example 1 provides a formal proof of the relationship between perpendicular lines and right angles. Study this proof, noting the order of the statements and reasons. The numbers in parentheses to the left of the statements refer to the earlier statements. Yeah, we'll study the proof. Strategy for the proof. We'll take a look at the proof, but we're not going to go through it in detail. All right, theorem. If two lines are perpendicular, then they meet to form right angles. Okay, so that's a theorem. Remember, theorems, we can prove theorems. We don't need to prove postulates. We don't prove postulates, but theorems, we can prove theorems. And definitions are just definitions. So in the sense that we're just calling the case where two lines meet to form congruent angles, we're saying that's perpendicular. However, as a consequence of the definition, a theorem is that, this is not a definition, the theorem is that if two lines are perpendicular, then they meet to form right angles. That doesn't have to be true. Based on the definition of perpendicular, that doesn't have to be true, but they're saying it is true, and we can prove it. And again, intuitively, it makes sense because you have a straight angle here, and if this line is intersecting here and it's forming congruent adjacent angles, well, then they have to, if they're congruent, then they have to sum to 180. That means they're going to be 90 degrees. And a 90-degree angle, that's a right angle. So there you go. Now, it's not quite as obvious on, well, then why does the other side also have to have right angles? And so I guess we'll see how they prove that officially. But this line does not all of a sudden change direction when it crosses through, or it wouldn't be a line, right? So since it's not, these lines aren't changing direction, or they wouldn't be lines, it has to be the case that the other side is also going to form congruent adjacent angles. All of the sides are. This is going to be congruent adjacent angles. This. It has to be. But that's not an official proof. I didn't officially prove anything there from a mathematical standpoint. Okay, so let's see how they prove it officially. Given that line AB is perpendicular to line CD, intersecting at E, so this is a definition, right? They're telling us that they're perpendicular. And so what does that mean? That's from a technical standpoint. What are we actually given here when they tell us this? What are we given here when they tell us that line AB is perpendicular to line CD? Well, what's the definition of perpendicular? That means that they meet to form congruent adjacent angles. So that's in essence what we're given. They're telling us that these two lines intersect and the adjacent angles that they form are congruent. Okay? So now we want to prove that angle AEC is a right angle, angle AEC. All right. So the lines are perpendicular. That means that angle AEC is congruent to angle CEB. Okay? Yeah, the adjacent angles based on the definition of perpendicularity. So since they're congruent, their measures are the same. We know that's the meaning of congruence of angles. And angle AEB is a straight angle because it's a line. Any angle on a line is a straight angle. And we know that measure of straight angles is 180 degrees. Okay, now the angle addition postulate, the measure of angle AEC plus measure of angle CEB is equal to measure of angle AEB. So since the two angles must sum to 180 and they're congruent, we're going to see that the measure of angle AEC is 90 degrees. They use the angle addition postulate and substitution, and then the division property of equality. Yeah, these are just all rigorous. They're rigorously stating exactly the property they're talking about, but this is trivial to non-mathematicians. Okay, so yeah, so it's the measure of angle AEC is 90 degrees, therefore it's a right angle. Because that's by definition. Okay, let's see. In figure 1.61, the sum of measure of angle AEC plus measure of angle CEB plus measure of angle, find the sum of all four angles. Well, okay, if we look here, the sum of all four angles is going to be 360 degrees because it's a full rotation. It's two straight angles. It's this angle, a straight angle, plus another straight angle, 360 degrees. So because each angle of the sum measures 90 degrees, the total, okay, so they look at this from the definition of perpendicularity, and that if these two lines are perpendicular, then they form congruent adjacent angles. But every one of these angles meets the definition of the lines being perpendicular. These are all, from the perspective of these two lines intersecting, these are all adjacent angles. And so all of the adjacent angles of two intersecting perpendicular lines are right angles. So they all are, there's 4 of them, so they sum to 360. But no matter what, even if these weren't 90-degree angles, it would still always be, if you go a full revolution, then the total sum is 360. In general, the sum of the measures of the non-overlapping adjacent angles about a point is 360. Yeah, exactly. The sum of the measures of the non-overlapping, and all the angles are adjacent, about a point is 360. Exactly. In general, it doesn't matter what, if you sum angle 1 plus angle 2 plus angle 3 plus angle 4, that's going to be, it's a full rotation. It's 360. They're non-overlapping, and they're all adjacent. And you go all the way around the point. The sum of these is going to be 360. All right, relations. The relationship between perpendicular lines suggests the more general but undefined mathematical concept of relation. Okay? In general, a relation connects two elements of an associated set of objects. Table 1.8 provides several examples of the concept of a relation R. Okay, so a relation connects two elements of an associated set of objects. Let's see what they mean here. Relation is equal to 2 plus 3 is equal to 5. That's connecting two elements of an associated set of objects. Is greater than, is perpendicular to, is complementary to, is congruent to, okay, is a brother of, okay, so yeah. Again, this is rigorous mathematical lingo here, but if you're, anytime you have I think this is common sense. Anytime you say, like, this is, how are two things related, right? And we've been doing that. We can say this is equal to this, greater than this. These two are perpendicular. These two are adjacent. Right? It's how two things are related to they're saying not two numbers, but two elements, whatever it is. Two figures, two numbers, two whatever. All right, there are 3 special properties that may exist for a given relation R, where A, B, and C are objects associated with relation R. The properties consider one object reflexive, 2 objects in either order symmetric, or 3 objects transitive. For the properties to exist, it is necessary that the statements be true for all objects selected from the associated set. These properties are generalized, and specific examples are given below. So yeah, this can get really mathy. The relations between sets and multiplication of, Cartesian multiplications of sets, things like that. And this really has to do with understanding math proofs. So, but okay, if 5 is equal to 5, the equality of numbers has a reflexive property. Okay, so 5, let's just note that. 5, if you have 2 numbers are equal to each other, that's the reflexive property. Symmetric is that, so if L is perpendicular to M, then M is perpendicular to L. It's kind of like it's reversible, the reversibility, it's kind of similar to that. But we're not talking about if-then statements here. We're talking about relations like perpendicularity. Or, if A is adjacent to B, then B is adjacent to A. If angle A is adjacent to angle B, then B is adjacent to angle A. That's a symmetric property. Okay, then the transitive property is like, so we know that numbers obey the transitive property. If A is equal to B and B is equal to C, then A must be equal to C, right? But okay, maybe that's not the case with congruence. That's the case for numbers. Well, that is the case with angles, so if angle 1 is congruent to angle 2, and angle 2 is congruent to angle 3, then angle 1 is congruent to angle 3. But maybe with congruence of other figures, they say congruence of angles has a transitive property, but maybe with other figures that's not the case. So that's the idea. We're going to see if these properties apply for different values and definitions. But again, this can get confusing. This is for mathematicians. What I've seen is that this is way more generalized when you're comparing sets. And so we're just going to glance through this and take a look at what it says and just try and note these ideas as we go through the textbook. Okay, does the relation is less than for numbers have a reflexive property, a symmetric property, a transitive property? So for numbers, so A is less than B. Does that have a reflexive property? No, because you can't, well, wait, okay. It doesn't have a symmetric property because you can't flip it. If A is less than B, then if you flip it, B is not less than A. Is it transitive? So if A is less than B and B is less than C, then A is going to be less than C. So it is transitive, but is it reflexive? So this would be good to think about what reflexive means. Because, oh, I see. Okay, yeah. You take the same number. If 2 is, so, okay, with equals, you have 2 is equal to 2. That's true. So with less than, 2 is not less than 2, so it's not reflexive. And it's not symmetric. We saw why it's not symmetric. But it is transitive. And now we can think about when it comes to is perpendicularity, L is perpendicular to M. The relation perpendicular, is that reflexive? Well, you would say, is L perpendicular to L? No. So it's not reflexive. Now, L perpendicular to M, I mean, that's just a definition. But can you flip that, though? Yeah, so it's symmetric. Now, is it reflexive? So if L is perpendicular to M and M is perpendicular to P, then is L perpendicular to P? That's interesting. So if L is perpendicular to M and M is perpendicular to P, well, no, because it's not necessarily transitive because P could be over here. They don't intersect. Or P could be out in a different plane than L and M, going like through. So no, not transitive. So yeah, it's pretty interesting. All right, congruence of angles or of line segments is closely tied to equality of angle measures or line segment measures by the definition of congruence. So, okay, the congruence of angles or of line segments, let's read this again. The congruence of angles or of line segments, that means they have equal measure, is closely tied to the equality of angle measures or line segment measures by the definition of congruence. Yeah. Well, we know that's part of the definition for congruent angles and line segments, that means their measures are equal. But that's not necessarily the case for, like, when we see, like, if two triangles are congruent, that doesn't mean they have equal measure, because what are you even saying when you say measure of a triangle? Like, it's area. So, but okay. Properties for the congruence of angles. Reflexive. If angle 1 is congruent to angle 1 and angle is congruent to itself, yeah. So, but less than, that wasn't true, right? It's also symmetric and it's also transitive. Now, this is just congruence of angles. This might not be the case for a congruence of other shapes. So as far as the congruence between angles, that obeys the reflexive, symmetric, and transitive properties. Any relation, such as congruence of angles, that has reflexive, symmetric, and transitive properties is known as an equivalence relation. In later chapters, we will see that congruence of triangles and similarity of triangles also have reflexive, symmetric, and transitive properties. Therefore, these relations are also equivalence relations. So, like equal to, for any two numbers, equal to it has all three properties. A is equal to A, and then if you have A is equal to B, you can flip that, and it's true, symmetric. And then if A is equal to B and B is equal to C, then A is equal to C, so it's also transitive. So that's the equals is an equivalence relation. Congruence of angles is equivalent, and they're saying that also congruence of triangles And similarity of triangles is also an equivalence relation. Equivalence relation is that all the elements, you could take any element, and with that, well, yeah, we're not talking about the elements, we're talking about the relation. So perpendicularity of lines, right? Once you state the relation, that kind of implies what the elements are. If you're talking about perpendicular, you're talking about lines. If you're talking about congruence, well, then you have to specify the actual elements in that case. You can't just say congruent, you have to specify. But yeah, so actually you can't sometimes just state the relation. You have to state the elements as well. But if you have a relation between elements and you state the elements and you state the relation, and for all of those elements in that relation, the reflexive, symmetric, and transitive properties are satisfied, then that's called an equivalence relation. Okay, returning to the formulation of a proof, the final example in this section is based on the fact that vertical angles are congruent when two lines intersect. See figure 1.62a. Okay, because there are two pairs of congruent angles, the proof could be stated. So yeah, we stated that vertical angles are congruent. Vertical angles are the non-adjacent angles of an intersecting group of four angles. Any intersecting lines make up a quad group of angles. Well, the ones that aren't adjacent are called the vertical angles, and we stated previously that those are going to be congruent, but we haven't proven it yet. So we want to prove that angle 1 is congruent to angle 3 and angle 2 is congruent to angle 4. Or, in other words, their measures are equal. Such a conclusion is a conjunction and would be proved if both congruences were established. Yeah, it's a conjunction in that it's this and here. You can't, if these are proved to be congruent but these aren't, well, then you can't say vertical angles are congruent. You're trying to prove that vertical angles are congruent. And to do that, we need to prove both of these at the same time, or else we can't prove that vertical angles are congruent. So, and that's what we said was a conjunction. All right, so prove angle 2 is congruent to angle 4. We're going to start there. Oh, yeah, so I guess we're just as an example, they're going to prove angle 2 is congruent to angle 4, but you could do the same thing to prove angle 1 is congruent to angle 3, but we're not going to do that for simplicity. So, okay. We have this theorem that if two lines intersect, then the vertical angles formed are congruent. That's not a definition. It's a statement that's a consequences of previous definitions and postulates. And now we want to prove this. All right. So we're given that line AC intersects line BD at point O. That's what we're given. So what does that mean? Since we're given that, what does that mean? What are we in effect given from a technical standpoint? Well, that means that if two lines intersect, they're going to intersect in a plane, and that means that you can have this quad group of angles formed. If we're assuming lines extending all the way infinitely, you're going to have this group of four angles. It could be if you had like two line segments intersect and they don't go all the way through, it could just be two angles, but we're thinking about lines intersecting at a point O, so we have this group of four angles, and they're going to be what else is a consequence of this statement, the given statement, that, well, we're going to have these supplementary angles, like 2 and 3 are going to be supplementary, 1 and 4 are going to be supplementary, 1 and 2 are going to be supplementary, 3 and 4 are going to be supplementary, because we have these lines here, straight angles. So that the straight angle is 180 degrees. So that's what we're given, right? That's the consequences of saying that a line intersects another line. All right, so now with that, we want to prove that angle 2 is congruent to angle 4. So, okay, we're given this, and as a consequence, we have these straight angles. So then, with the angle addition postulate, let's see. Measure of angle 1 plus measure of angle 4 is equal to measure of angle DOB, and measure of angle 1 plus measure of angle 2 is equal to measure of angle AOC. And yeah, that's just what they're, so you would think measure of angle 1 plus measure of angle 4 is equal to DO, oh no, that's right, yeah, DOB, yeah, that's right, okay. And then measure of angle 1 plus measure of angle 2 is AOC, and measure of angle 1 plus measure of angle 4 is equal to measure of angle 1 plus measure of angle 2, because that's two straight angles. And then you could subtract the measure of angle 1 from both sides, get measure of angle 4 is equal to measure of angle 2. which means they're congruent. Since their measures are equal, angle 4 is congruent to angle 2, but then the symmetric property, you can state it both ways, which is, it's really technical math stuff there, but yeah, there you go. But we're not going to do the proof for the other vertical angles being congruent 1 to 3, but you could do the same thing. So that means you've proven that vertical angles are congruent. Any vertical angle, no matter what the situation, two lines intersecting in any plane in 3D space, you're going to naturally form two pairs of vertical angles, and it's been proven now that vertical angles are congruent in all cases across the board. All right, in the preceding proof, there is no need to reorder the congruent angles from statement 7 to statement 8 because congruence of angles is symmetric. In the later work, statement 7 will be written to match the proof statement even if the previous line does not have the same order. The same type of thinking applies to proving lines perpendicular or parallel. The order is simply not important. So yeah, they're saying this was redundant even from a technical math standpoint, saying they're symmetric so you can flip it. Okay, now more constructions. In this case, it's with perpendicular lines. These are pretty interesting. You kind of feel like you're going back to the fundamentals of geometry, the way the Greeks did it. Construction 2 in section 1.2 determined not only the midpoint of segment AB, but also that of the perpendicular bisector of AB. Yeah, right. In many instances, we need the line perpendicular to another line at a point other than the midpoint of a segment. So, okay, in section 1.2, what we did was we had a line segment, and we wanted to construct its midpoint. So we took a compass and put the center of the compass here, and then set the radius to something that was definitely past what we could visually see was the midpoint. So maybe set the radius to this. Okay, and then with that, we drew and we put the center here and then drew an arc at that radius that just, you made sure it kind of went past the midpoint. Then you put the center here, didn't change the radius, put the center here, did the same thing, and you got another arc, and then where those intersected, you could connect those two lines, and that was going to go through the midpoint of the line segment. I didn't draw this correctly here, but now they're saying, but the only goal there was to get the midpoint. There's the midpoint of the line segment. But now they're saying that we can use the same procedure to get, like, we also have a perpendicular line here. That was all. They're saying that also what we were doing was drawing the perpendicular bisector of that line segment. Okay, so to construct the line perpendicular to a given line at a specified point on the given line. So, okay, given line AB with point X, okay, construct a line EX so that EX is perpendicular to AB. So I guess X is not necessarily the midpoint of AB, or maybe it is. It doesn't have to be. We're just trying to construct a perpendicular. So let's see. Construct a line EX so that, yeah, okay, construction. So from figure 1.63b, oh, no, okay, we're starting here. So we have line AB, and here's point X, and they didn't state this has to be the midpoint. We want to construct a line that's perpendicular to AB going through X. So what they do is, using X as the center of the compass, mark off arcs of equal radius on each side. So set the radius to something, in between, not past A. Draw an arc, and then don't change the radius. Draw an arc over here with the same center. Okay. Now, using C and D as centers, mark off arcs of equal radii with a length greater than XD so that these arcs intersect either above or below line AB. So you're going to put the center of the compass at C and D and make the radius bigger than what you had it before, drawing XD and XC. And then you're going to create arcs either above or below line AB, wherever that intersect. Put the center at C, put the center at D, and then draw these two arcs. And then calling the point of intersection E, draw EX, which is the desired line. And so in that case, EX is going to be perpendicular to AB Interesting to think about why that construction is correct. Like, why are you guaranteed to get a perpendicular line? Like, what caused that to happen? Why are we guaranteed to have a perpendicular line in that case? That's something we might talk about later, but try and think about that on your own. All right, the theorem that construction 5 is based on is a consequence of the protractor postulate, and we state it without proof. Okay, so here we're going to get some insight into why this works. In a plane, there is exactly one line perpendicular to a given line at any point on the line. Okay, so let's read this again. In a plane, there's exactly one line perpendicular to a given line at any point on the line. So what they're saying is, in a plane, right? So you have to, we're in the plane of the page here. You have a line AB. If you pick any point on that line, then there's only going to be exactly one unique line that's going to be perpendicular to the line AB that also goes through X. And so with that, it was something to do with the way the way we drew all of this. We forced that line going through X to be the perpendicular line. To me, it was something to do with the fact that these 2 points were equidistant from X, and we could have just left the radius as it is, and we've gotten the same result. But they probably want to illustrate that wasn't a requirement. So they said you can change the radius and then go to C and D, but make sure that you draw the arcs up here from C and D with the same radius. And because of that, those two equidistant, like the C and D is equidistant from X, and then E is equidistant from C and D. That forces the line to go through straight up and down. It's that equidistant, like every single point on here on the line is equidistant from any point, like, and that's another way of looking at perpendicularity, right? So we're going to learn more about this. We're going to get more insight on why this construction worked as we go through the textbook. I think when we study triangles, it's going to shed a lot of light on this. Okay, let's see. Construction 2, which was used to locate the midpoint of a line segment, that's what we just talked about, is also the method for constructing the perpendicular bisector of a line segment. Yeah, so in this, what we just learned in construction 5 was how to construct any perpendicular. X over here, X wasn't necessarily the midpoint of the line segment. It didn't matter. We could have made it wherever we want, just as long as the only requirement was that these radiuses were equal. We could have made those radiuses wherever we want, or we could have picked point X to be wherever we want, and done the same process. If put point X here, set the radius of the compass equal to this, and then draw the same arc over here, and then put the center here, change the arc length or the radius length, and same idea, right? But now they're talking about, this was the specific case where we found the midpoint, but at the same time we found the perpendicular bisector, because we couldn't. You might say, well, couldn't we have just, there's the midpoint, and now do what we just did in construction 5, set the radius. Well, no, we don't know where the midpoint is. We can't just arbitrarily pick a point. So we have to do it. Let's see. In for XY is perpendicular bisector of RS. The following theorem can be proved by methods developed later in this book. So, the perpendicular bisector of a line segment is unique. Yeah, so like in a plane, the perpendicular bisector, and that makes sense based on this theorem. There's exactly one perpendicular line to a given line at any point on the line. Well, we know the midpoint of a line segment is unique. There's only one midpoint, and so in that case, there's only going to be one perpendicular bisector, one unique perpendicular bisector. All right, now, if we think about how we constructed this, where we put the center of the protractor at R, made the radius bigger, clearly past the midpoint, and then they drew an arc, and then didn't change the radius, came to the other end and drew another arc. So why does this work to make the perpendicular bisector? Well, informally, it's something to do with the fact that you're constraining the line to where, like, if you picked a point on the line and you had the same angle going down to the horizontal line, you're fixing these distances to be equal. They have to be equal. And that's something that what's another way of viewing what perpendicular means, which we're going to learn, like they're saying here. We're going to learn more about this later as we go forward in the book. Okay, so let's work some example problems.